the discriminant. Okay, make friends. It is your absolute new best friend. It is so useful when we're dealing with quadratics and we're dealing with a third unknown. So in this lesson, we're going to run through a couple of things with discriminant. First, where does it come from? What is it? And how do we sort of understand it? And then we're going to extend that, looking at how we use a discriminant when we're working with intersections between curves and straight lines. It would help if I had my pen plugged in. I might actually be able to write more. Right, so the discriminant. The discriminant hides in your quadratic formula. So x equals minus b plus minus square root b squared minus 4ac all over 2a. And you can use this if you're to solving any quadratic, okay? So yes, we do focus on factorizing to solve because it is quicker, it's more efficient, and it's much more straightforward a lot of the time. But the power of the discriminant is that you can solve. The power of the quadratic formula is that you can solve any equation. So factorizing is for equations that can be factorizing. The formula is for any quadratic. And what sits in here then is a little piece. We're taking the square root of b squared minus 4ac every time we do this. Now remember also that we're talking here about ax squared plus bx plus c equals 0. So we're working with our traditional coefficients for our quadratic equation. Now, when we take the square root of b squared minus 4ac, there are 3 different options for what our answer could be. And those 3 different options have a dramatic impact on the answers to this equation that we're solving, this ax squared plus bx plus c equals 0. And that is why the discriminant is such an important piece in understanding the roots for the quadratic. So it's not going to give us the answers, it's going to tell us about the answers. So if we think about it, we say there's 3 different options for what the answer to that b squared minus 4ac could be. So we could have a positive result. We could have that b squared minus 4ac equals 17 or 24 or 2.5 or 3.172. I mean, who knows what we're working with in terms of coefficients here, but it could be positive. So we're taking the square root of a positive number, everything's happy, we would get plus and we would get minus, we get an answer coming here and we would be plussing it or minusing it, and it makes sense, okay? We've got a number, right? What happens if b squared minus 4ac equals 0? Okay, well, now there's nothing. We've got the square root of 0 is 0. There's nothing to plus or minus to our minus b. So it would be minus b plus 0, minus b minus 0. No change to that minus b, okay? So what if then our b squared minus 4ac was actually a negative value? So in this case, we're trying to do the square root of a negative number, square root of minus 9. Not going to work until you get to the end of A-level maths and you're working with complex numbers and imaginary things, okay? So at this stage, square root of a negative number doesn't exist. So what happens then? Well, then we can say we can't solve this quadratic because there is no solution. Our calculator just says error and we don't know what to do. Okay, and it's because we've got that negative number coming in underneath that square root sign. Can't do it. So these are our 3 different situations, and they actually have implications then for the answers for our quadratic. So if we write this now a little bit more technically, we can have b squared minus 4ac is greater than 0. There's our positives. We could have b squared minus 4ac is equal to 0. There's our equal 0. And we could have b squared minus 4ac is less than 0. So that, of course, is then our negatives. So positives or 0 or negatives, what effect does it have? Well, if we think about it, if we have minus b plus a number, minus a number, Well, we're going to have two different answers. So the answer to our quadratic would be two different values. Okay, minus 2.41 and plus 3.61. Who knows, okay? You've seen a lot of quadratics with two answers. That, of course, is coming from your positive square root. So we would have two distinct real roots. Remember that a root is an answer to a quadratic equals 0. Okay. If b squared minus 4ac equals 0, so now we would do minus b plus 0 minus b minus 0 is just minus b over 2a in this case. So you've got the same answer, but you got it twice. Because technically you had minus b plus 0 over 2a, and you had minus b minus 0 over 2a. So you got the same answer twice. So here we would say that this is one repeated real root. And our last one, now we're doing minus b plus the square root of doesn't work, negative number. Okay, so we're going no answer, error on the calculator. So when b squared minus 4ac is less than 0, the technical response here is that there is no real roots. So we can have three different situations, three different answers to our quadratic. And we've got two distinct real roots, two separate different answers, one repeated real root. Is it going to be 1 twice? Is it going to be 2.5 twice? Okay, or we've got no real roots. We can't answer this quadratic equation. There's something fundamentally wrong. So what does it look like? Okay, how does this relate? Remember, we're saying that we're trying to solve a quadratic equals 0. Okay, so let's say there's our x-axis, of course, where quadratic would equal 0. So two distinct real roots. Beautiful. Two distinct real roots. Get some color going. We would have one answer here and one answer here. One repeated real root. Where is it going to be? It's going to be sitting up here. So we've got an answer. We get an x equals something, but that something happens twice. So it happens there as we touch that axis. Our last situation where we have no real roots, in this case we would have our x-axis, same like before. But what we're saying is that quadratic never equals 0. There's no real root. The quadratic never touches. It never actually has x squared, ax squared plus bx plus c equals 0. It doesn't happen. It doesn't exist. So therefore, our quadratic must sit completely above that x-axis. It doesn't touch it at all. So we can have two distinct real roots, we can have one repeated real root, or we can have no real roots. And that also gives us an understanding of where our quadratic is sitting in relation to our x-axis. So let's put this now into sort of real terms. See how much we can fit on one whiteboard here. So let's consider we have x squared minus 4x plus k equals 0. Now, the most common use of the discriminant is to solve for an unknown like this. Okay, we have only one equation, but we have two variables. We've got a problem. But what we're going to do here is we're just going to understand this, okay? So if we said that this equation here had two roots, then we would be saying that, so for two roots, we would be saying that b squared minus 4 squared minus 4a is 1, c is k. And we'd be saying that all of this is greater than 0. Here, we would get to one repeated root. So here we would have minus 4 all squared minus 4 times 1 times k, so b squared minus 4ac, but it would equal 0. Okay, and in the last one, we would have minus 4 all squared minus 4 by 1 by k. Still b squared minus 4ac, but now it is less than 0. So we would have 16 minus 4k greater than 0. We would have 16 minus 4k equals 0, and we'd have 16 minus 4k less than 0. So it's always the same thing where we're looking at b squared minus 4ac, okay? But now let's have a think. So here, if we solve this, k comes on this side, less than, and it would be 4. Here we would have 4 equals k, and here we would have 4 is less than k. Right, so what does that mean? Okay, so obviously 4 is our magic number in this case. Okay, so what it means is that if we're going to have one repeating real root, our equation would have to look like x squared minus 4x plus 4 equals 0. That is the only way that this equation is going to have one repeated real root. If this equation has a k value that is less than 4, the equation could have two distinct real roots. Okay, so for example, we could have x squared minus 4x plus 3 equals 0. Okay, we could have x squared minus 4x minus 5 equals 0. Any value that is less than 4 is going to give us two distinct real roots if we were to solve it. On the flip side of the coin, what values of k would we have that give us no real roots? If we had the equation of x squared minus 4x plus 8 equals 0. There, our k is bigger than 4, so we're going to have no real roots. Okay, if we had x squared minus 4x plus 5 equals 0. Again, k is bigger than 4, so we're going to be above that x-axis. And what's really nice is we're going to tie in here and this understanding of location when you get into transformations as well, because we're transforming our functions and we're transforming quadratics. It can be very helpful to have this understanding of this relationship with this x-axis. So you've got this concept of we have different numbers of roots, we have different numbers of solutions, different numbers of answers to our quadratic, and that is affected by these values of b, a, and c that come out of our standard ax squared plus bx plus c equals 0. So we have all these different situations. So the next thing then is, how do we use this for something like an intersection? So here we're actually going to consider a past paper question. Okay, so paraphrasing, we have a line y equals x over k plus k, which is a tangent to the curve for y equals x squared at p. They want to know the value of k, and they want to know the coordinates of p. So where does this all happen? This is Winter 2012, paper 12, question 4. So we have a look. We have a straight line, we have a curve. Okay, that's cool. We have a y, an x, and a k. We've got 3 variables. So for part 1, finding that value of k, we've got a problem, because when we have 3 variables, we would need 3 equations to solve them. Two equations can only solve us 2 variables. So we need to think about this a little bit differently. And this is where our discriminant comes in. Okay, so let us think a little bit about, the situation that we've got here. Okay, so we've got, let's answer in a different color, it makes life more interesting. Got beautifully straight drawn with a ruler, y and x axes. Now, for y equals x squared, well, this is y equals a quarter x squared. So we know then that we're just working with x squared and he's just a little bit different. So we can draw him like this. Y equals a quarter x squared. There's our curve. Now the thing about this line is we don't know where it sits. Okay, so the line could sit here. Let's make ourselves a little bit more space. So that could be our line. This could be y equals x over k plus k. We can see it's got a positive gradient, it's got a positive k, a positive intersection. I mean, who knows where it sits, okay? Our line could also sit somewhere else. Okay, considering this line that it's sitting like this, it could sit parallel to it, but it could sit there. This could be y equals x over k plus k. But it could also sit way down here. Maybe k is negative. Y equals x over k plus k. Well, if k was negative, actually it would sit the other way around, wouldn't it? Because then our gradient would also be negative. But you get the idea, okay? We have different positions where this line could sit, and that leads to different arrangements of intersections between the line and the curve. We could have two intersections, or we could have one intersection, or we could have no intersections. And now this is sounding rather familiar. This is sounding a bit like the discriminant, 2 or 1 or none. And if you think about it, that one intersection, its tangent is actually repeated. This here is your tangent. So we're now looking at a way that actually we could maybe use a discriminant to work with intersections. And it is a wonderful thing that our discriminant does work for intersections. So if we have b squared minus 4ac is greater than 0, if we have b squared minus 4ac equals 0, or if we have b squared minus 4ac is less than 0, we would have two intersections, one repeated intersection, which I just mentioned is your tangent, or we could have no intersections. So what we have to do though, obviously, we can't use our discriminant on our curve, we can't use our discriminant on our line, because those are two independent things. So whenever we want to use a discriminant to work with intersections, first we have to build that function, that equation that represents the intersection. So what we're first going to do is intersect them, okay, and get this unknown with this k in it, because we don't know what that quadratic is going to be. It's going to have this k value in it that is unknown. And then we're going to work with our discriminant. So if we have a look now at actually solving that, so we have y equals x over k plus k, and we have y equals x squared over 4, so we can make our lives rather easy. So part 1 asked us to find the value of k, but they told us that the line is a tangent to the curve. So we can say, okay, well then that means that x over k plus k is going to equal x squared over 4, right? We're getting this idea that the two of them interact. They're going to intersect in some way, shape, or form, or not, depending on our discriminant. So let's now get this into a standard ax squared plus bx plus c equals 0. So we'll multiply through by a k. So we have x plus k squared equals kx squared over 4, and then a 4x plus 4k squared equals kx squared, everybody on one side, kx squared minus 4x minus 4k squared. So we've got now this equation of intersection, and it's a quadratic, but we don't know where that quadratic sits because we have all these unknown values of k in here. Okay, we've got a kx squared and we've got a 4k squared. And that means that, okay, we have a quadratic that's representing this intersection between this line and this curve, but we don't know where it sits. We would need to know that value of k in order to be able to know where our quadratic sits in terms of then where does our line and our curve intersect. So we're told there's a tangent, so therefore we know that b squared minus 4ac equals 0 for a tangent. So we can work off this piece of information. We can say then, because remember when you use a discriminant, okay, there's no x's and there's no y's in there. There is only coefficients. B, A, and C are your coefficients. So b squared minus 4 squared minus 4, A is k, and C is minus 4k squared. And we know that equals 0. So always be careful of your signs. You want to make sure you're taking your signs with you properly when you're doing this. So minus 4 all squared gives us 16. Minus 4 times minus 4 is plus 16. K times k squared gives us k cubed equals 0. So 16k cubed equals minus 16. K cubed equals minus 1. Cube root of minus 1 is minus 1, so k equals minus 1. So because we had that information about the interaction between the line and the curve, and we got this interaction to a quadratic, we can then use the discriminant to look at the intersections. If the intersections are a tangent, it equals 0, and we can solve for k. So now we know that k equals minus 1. So part 2 of the question asked us now to find the coordinates of P. So now that we know that k is minus 1, we actually know that we've got a whole different line to what was going on, because now we know that our line is y equals minus x minus 1. So actually, the version of the line that we're working with is something over here, where that is now minus 1, gradient is a minus 1, and we have one repeated root, one repeated intersection. Okay, so we have now our equation of our line. Okay, we're looking for our coordinates of P. So what we need to do is, where does our line meet our curve when k is minus 1? But remember, we've already done line equals curve. We've got that equation. It's this one here. So what we can then do is part 2. We know that 0 equals minus 1 x squared minus 4x minus 4 minus 1 squared. Note the brackets for the substitution of a value. Be careful. So 0 equals minus x squared minus 4x. This then is still minus 4, because minus 1 squared is plus 1. So we're going to be solving, and we're just going to move everybody onto the other side, so we have a happy x squared, much easier to factorize. Okay, then we can go for it. 4 is an easy one because it's factors of 4 that add to 4, well, 2 and 2. And they are both positive. And there's the magic. We said this was a tangent. We said this was a repeated root. And look at that. We get the same answer twice. So we know that x equals minus 2 twice. So now if we want the coordinates of P, we're going to need to have the y value as well. So y equals, remember, we have minus x minus 1. So minus 2 minus 1. So y equals 2 minus 1, which is 1. So the coordinates of P equal minus 2, 1. So we're using that information that we've been given And we are being very, very careful of our signs. This question is a wonderful example of the importance of brackets and importance of watching your signs, because there's so many negative numbers going on, and it's so simple and so easy to make a little mistake with a sign, and then it just knocks you out completely for the rest of the question. So it's really important to be in that habit of taking the sign with a value or with a variable, whichever you're working with, signs go with, and you always substitute using brackets to keep those signs safe.